Hey everybody. Today we're going to do a couple chemical reactions. Finally, right? We're in a chemistry class. We've been learning all about chemical compounds. We're finally at the point where we can mix chemicals together and see what kind of things happen. But before we do, we want to have some thought about what's going to happen before we just go willy-nilly mixing things together. So we're going to predict some chemical reactions using a couple tricks. We're going to break them into the three main categories of chemical reactions. You should have already watched a video about that. It's acid-base, redox, and precipitation. We're going to start with precipitation reactions because they're visually interesting, and I also think they're the easiest to predict the products for. Some of these are in your types of reactions lab, and some of them are not. But let's go ahead and take a look at a few. This one is in your types of reactions lab. It is reaction number 10. And the reaction is silver nitrate with sodium phosphate. Now the first thing we need to be able to do in order to predict our chemical reaction is we need to be able to determine what chemical compounds we're talking about. And we need to have good chemical compounds. That is to say, when I mention silver nitrate, we need to make sure we know the typical charge of silver, the typical charge of nitrate, and the chemical formula of nitrate. If we get something wrong in the charge balance of our compound, we'll end up not predicting our chemical reactions correctly, or we'll come up with something that we can't properly predict. So, first thing, we have to be learning our common polyatomic ions and our chemical names, our nomenclature. So, silver nitrate. Using your common ions list, hopefully you can get that silver nitrate is AgNO3. And we're going to add to that sodium phosphate. Sodium's Na, phosphate is PO4. Now, phosphate is a -3 charge, so in order to have a good compound, we need to have Na3PO. After we have our two compounds, we're going to want to have our periodic table handy for predicting whether these are going to be aqueous or solids when we put them in water. You should be familiar, at the bottom of the periodic table, you've got your solubility rules. These, let's say solubility guidelines, but these will help us predict whether each of these compounds is going to be aqueous or solid. Now, nitrate compounds, in our solubility guidelines, rule number 2 says nitrate compounds are always soluble. So that's one that's actually, in my opinion, worth remembering. If you see a nitrate, it will dissolve in water. If there's no water, it'll be a solid. But if there's water, it'll dissolve in water. Another really good one to remember, sodium compounds are always soluble in water. So that is looking at, again, our solubility rules. Rule number 1, group 1 ions, lithium, sodium, potassium, and ammonium are soluble. Particularly, sodium compounds are always soluble. So now we can put these two things into solution together, and we can kind of imagine what's going to happen. The silver and the nitrate are going to split from each other, and they're going to float around in solution. The sodiums, all three sodiums are going to split up from the phosphate, they're going to float around in solution. And what we want to consider is what happens when the phosphate bumps into the silver, what happens when the nitrate bumps into the sodiums. What we're going to look at is what happens if we switched our cations and what happens if we switch our anions, right? This is just trading charges with each other. The positive and the positive aren't going to go with each other. So I'm going to take my silver and put it over here, and I'm going to take my sodium and I'm going to put it over here. This is predicting the products. This is called a metathesis reaction. Double displacement is also an appropriate name, or if you're like me, you just call it a flip-flop reaction. Because I'm going to flip, I'm going to flop. So I'm going to make silver phosphate, putting my silver over where the sodium was, and I'm going to make sodium nitrate, putting my sodium over where the silver was. Flip and flop. Now, back to our solubility rules. Oh, first, before we get back to our solubility rules, again, we have to charge balance. Sodium's +1, nitrate's -1, so that's charge balanced. Here, our silver's +1, our phosphate's -3, so I'm going to need 3 silvers on that phosphate in order to charge balance. After we've got that charge balance, now we can go ahead and consider, well, which of these things is going to be soluble, which is going to be insoluble. That is to say, which will be aqueous, which will be solid. The sodium nitrate, it's got sodium, it's got nitrate, that is going to stay in water. So that means when our sodium bumps into our nitrate, nothing really happens. It's not very interesting. But when our phosphate bumps into our silver, if we look at our solubility rules, insoluble rules number 5, phosphates are insoluble. There's a couple exceptions, but generally, phosphates are insoluble. So we'll put an S behind that to say it's solid. This is our prediction of what will happen if we mix these two things together. And we'll do that in just a moment. Before we do, though, let's look at another example of how we do this kind of flip-flop reaction. I'm going to leave myself a little bit of space because we're going to talk about something else we can do to simplify this type of reaction. So the second reaction we're going to look at is copper chloride mixed with sodium carbonate. And I've got to be more specific than that. Copper 2 chloride mixed with sodium carbonate. So in this case, our chemical reaction CuCl2, remember the copper 2 chloride tells us the charge on copper. We need the 2 chlorines to charge balance, plus sodium carbonate. Do you know what carbonate is? Carbonate has a -2 charge, so I'll need 2 sodiums there to charge balance it. Sodium compounds, soluble, one to remember, right? Gives us a lot less to look up if we remember sodium compounds are soluble. Copper and chlorine compounds, though, those don't have easy to remember. So we're going to look at our rules. And rule number 3 says chlorine, bromine, and iodine are typically soluble. They usually dissolve in water, except with silver plus, lead 2 plus, copper plus, and mercury 2 plus, which is really mercury plus. So copper plus is not the same as copper 2 plus. Copper 2 plus will actually dissolve. It's not one of the 4 exceptions we have. Copper plus, copper 2 plus are different things. So this will dissolve. And now we can go ahead and do the same flip-flop metathesis reaction, switching the things back and forth, switching our cations with each other, and we're going to make copper carbonate and sodium chloride. Sodium chloride, aqueous, also already charge balanced, right? We've got the sodium with the +1 charge, we've got the chlorine with the -1 charge. That will already be charge balanced. Here, copper 2 plus, carbonate 2 minus, already charge balanced. So in this case, we're already charge balanced. According to our solubility rules, solubility or insoluble rule number 2 says carbonates are insoluble. So that should form a solid. This means in both of these reactions, adding together 2 liquids, we end up forming a solid. Adding together 2 liquids, we end up forming a solid. These are both referred to as precipitation reactions. Let's go ahead and look at the chemical reactions we just wrote down. The first one is silver nitrate with sodium phosphate. And as you can see, Both of these are already aqueous, just as our solubility rules predicted, but it's nice to have physical, real-world confirmation of those predictions. And what we're going to do is we're going to transfer some silver nitrate into the test tube, just so we can have it be a little bit more dramatic. Here is our test tube with silver nitrate in it, and to that we're going to add the sodium phosphate. We want to see if we have a noticeable change. Yeah, that was a pretty noticeable change. Right away, we're forming this silver phosphate precipitate. And what you can see is that it forms a kind of cloudiness. It doesn't look like a solid is necessarily forming, but that's because we're forming a solid on the atomic scale, right? We're actually just forming little grains like a really fine dust. And as we let it sit longer and longer, you can see the solids start to settle to the bottom. So we've definitely formed a solid. We could keep adding more sodium phosphate to this and see if we can form more solid. Oh yeah, see, there's more solid forming. Now at some point we won't form any more solid, and that's because we need to think about not just will a reaction happen or not, but how much does the reaction happen? That gets into the idea of stoichiometry, extent of reaction, and we'll talk about that next time, or next week. Our second reaction is the copper chloride. Copper is an interesting solution. It has this faint blue hue to it. That is from the way that copper behaves in water, copper ions. And to that, we're going to add carbonate, particularly sodium carbonate, but according to our net ionic equation, the part that matters is the fact that carbonate's going in. And you can see copper carbonate, a nice dense solid being formed. Has that nice kind of flakiness to it, almost has a little shimmer to it that I can see. I don't know if that's going to show up on the camera, but that solid we're forming, that's the copper carbonate. We can see that a solid is really being formed, and at some point I will have added so much carbonate that no more solid forms. And if I add too much, right, things aren't infinitely precipitatable. We got to think about the stoichiometry. They're also not infinitely soluble. That is to say, you know, at some point, if I put this into 10 gallons of water or more, the solid is going to start diluting again and breaking apart. That gets into ideas again that we cover in Chem 128, 125. But definitely, just from our simple predictions using the solubility rules, we have this kind of gelatinous blue crystals formed in our solution that used to be a faint blue. And if we let this sit, those crystals will settle out. As you can see, our silver phosphate that we formed earlier, we still have some cloudiness up here, but just letting gravity separate it, we've got a lot of solid collecting down at the bottom. So those are our two precipitation reactions that we did as examples. When you go to do your types of reactions prediction, you'll want to look for these types of behaviors. Was it two clear solutions? Did solids form? In an observational way to predict whether a reaction is happening or not, or if it's a precipitate reaction. here is our first acid-base reaction to consider. It is perhaps the most iconic of the acid-base reactions. You've got hydrochloric acid with sodium hydroxide. It is the definitive textbook case of an acid-base reaction. It's going to do things that are pretty similar to what we just saw with the precipitation reactions, where we're going to be doing that kind of flip-flop idea. We're going to recognize that this is going to be like a Cl- with an H+, even though, and I'm going to change that. This is going to be a delta minus and a delta plus, right? That partial positive, that's a polar covalent bond. This one is actually ionic. This is a full minus with a full plus. We've got an ionic bond here. This is technically a covalent bond. And this is also why we have to learn our list of acids and bases on that common ions list. At the bottom, you've got common acids and bases. It's important to know our common acids because those are going to be situations where the difference in electronegativity is large enough that water can interfere that covalent bond, and actually that covalent bond will disassociate in water. Here, we're actually looking at a chemical reaction of the sodium hydroxide with the hydrochloric acid. We're going to do a flip-flop. I'm going to bring the H over to where the Na is and the Na over where the H is, and I'm going to make HOH, and I'm going to make NaCl. We already know that NaCl is going to be aqueous, but what's this HOH, right? This is taking this H and replacing it over there. Well, HOH is actually just a silly way to write H2O. 2 hydrogens, 1 oxygen. Writing it as HOH kind of accentuates the fact that you've got a hydrogen interacting with an OH. But this is H2O. This is all covalent bonds. So this is actually going to become a liquid. And it's going to stay together. We don't break apart liquids. So this gives us the kind of really clear signs of what we look for in identifying an acid-base reaction. We're looking for an acid reactant, and we're looking for a water product. That doesn't guarantee that it's going to be an acid-base reaction, but those are the big signs that we're looking for to tell that an acid-base reaction is happening. The reason I don't do it in terms of the base is because those of you that are going on to biological sciences, or if you're taking Chem 129 or Chem 126, our definition of base needs to get more interesting, right? This is looking at the simplest versions of acids and bases. So at this level, it's going to be easier to identify the acid as a reactant and water as a product. Okay. Second reaction that we are going to consider. This is actually a reaction we're going to be doing in about a week when we're looking at titration, when we're doing the titration lab. We're going to look at acetic acid plus sodium hydroxide. The sodium hydroxide we already know. Sodium hydroxide is aqueous. What's acetic acid? Look it up on your common ions list. I like to write it this way because this COOH is giving us some information about the functional group right. We saw this when we were looking at our VSEPR drawings, trying to get three-dimensional geometry. COOH, that doesn't mean oxygens are next to each other. That means this carbon is next to 2 oxygens, COOH. This is trying to suggest what the functional group is and how we should write this compound. Other ways you might see it written, you might see it as CH4O2. C2H4O2, same thing. Or you might even see it as HC2H3O2. This is trying to get that H kind of out front to really accentuate the fact that it's an acid. But I feel like this is halfway to explaining it. And I really like this fully writing out the carboxylic acid group on the end. Now, we're going to do the same thing. This is an acid. So this hydrogen, the acidic hydrogen, is going to be the one that's in the carboxylic acid group. Carboxylic acid is acidic. That hydrogen is going to replace the sodium, and the sodium is going to hop over. Flip-flop reaction just like we had before. We are going to get and H2O liquid. Again, you'll notice we always put the cation first, so cation goes before anion. And this is ionic bond, so we're using the ionic trends for that. None of our covalent bonds broke, with the exception of that weird superpolar part with that delta plus and delta minus, that difference in electronegativity right next to each other. That's what gives rise to the acidic behavior. And we've got water as a product. So what we're typically looking for in our acid-base reactions. The last ones that I want to do, these are for the reactions today for our types of reactions lab, is looking at sodium carbonate with hydrochloric acid. So we'll have HCl plus sodium carbonate, not sodium bicarbonate, sodium carbonate. I'm going to go ahead and put this as sodium carbonate aqueous. We'll see that when we do this reaction, we're actually using a solid. But whenever we write a chemical reaction, we're really trying to represent what is happening as we mix things. We're trying to imagine if we could pause time and represent this dynamic situation. The reaction is going to happen only after this disassociates in water. So we want that aqueous part there to really accentuate the fact that this thing's going to rearrange. This is going to give us, if we just do the same flip-flop thing, we're going to run into a little problem with carbonates. Carbonates get an extra special rule associated with them, which is why I wanted to do this example. The hydrogen is going to come over, the sodium is going to flip, so we're going to have HCO3 plus NaCl. That's, of course, going to be aqueous sodium chloride. In order to charge balance this, we're going to have H2CO3, carbonic acid, and this does something special. At room temperature, under normal atmospheric conditions, H2CO3 naturally decomposes into H2O liquid and CO2 gas. This is part of carbonation and how soda can become acidic. This is part of why CO2 in the atmosphere can cause acidic conditions, because if it can go this way, it can go back. But carbonic acid will decompose into CO2, or if you put CO2 in a tight container with water, you can form carbonic acid. Since we're doing this in the open atmosphere, this is going to go to H2O in CO2. So this formation of the H2CO3 breaks apart. Let's go ahead and do these reactions and take a look at them. Let's go ahead and look at the acid-base reactions we were just talking about. So here we are going to be using 2 molar hydrochloric acid. That's the concentration of HCl in this aqueous solution. And we're going to be using 2 molar sodium hydroxide. Again, the concentration of sodium hydroxide in the aqueous solution. Now, we know a chemical reaction is going to happen, but unfortunately, these acid-base reactions are a little bit boring, right? You're going from two clear solutions to a clear solution. It does warm up a bit. Actually, it warms up quite a bit because the reaction is releasing heat and energy. But in order to make something that's visually interesting and visually detectable, we're going to be using indicators. These are special chemical compounds that change their color based on the pH of the solution. Phenolphthalein is a very common indicator. We'll be using this one in our stoichiometry lab. And I'll also show you how methyl orange changes. We'll be using this one in our carbonates lab. Now, phenolphthalein in our acidic conditions, just a few drops. Oh, I might have put too much. Weird. It's not supposed to have cloudy like that. My guess is there was some contamination in there. I should have cleaned these first. But phenolphthalein in acidic conditions has one particular color. And then as we add the sodium hydroxide, you see the sodium hydroxide turns it that bright pink color, but I didn't add enough sodium hydroxide to completely react the acid away. So it goes back to clear. Right? That's getting to the idea of extent of reaction. And a little shake. Once the solution stays pink, I'll know that all of the acid has reacted, and I've got excess base. Phenolphthalein makes it so we've got this nice visual change associated with it. Methyl orange does the same thing, except its color range is a little bit different. So when we put methyl orange into acidic conditions, it's got this dark reddish orange color. And as we add sodium hydroxide, we should see that change. Goes to an orange color, right? That bright red disappears. And we get this nice orange color when we're in basic conditions. Methyl orange actually goes through a couple different colors, but using strong acids and strong bases, it's too difficult to see. For our acetic acid, we'll go ahead and use phenolphthalein. This is the typical indicator we use for most acid-base reactions, unless we want a very particular change. But a lot of situations, phenolphthalein works really well. So I'll just put in 2 drops of phenolphthalein, not trying to overdo it like I did last time. So acetic acid is one of those funny compounds that goes by many different names. Acetic acid is its common scientific name. Ethanoic acid is the correct scientific name, but most of us just call it vinegar. Acetic acid is the active part of vinegar. And so we can see that it's acidic conditions. I added phenolphthalein. It's got that little bit of cloudiness, but it's still not pink. And then as I add sodium hydroxide, it goes pink. So that shows, oh, and that didn't take very much sodium hydroxide. Let's see there. Shake it around, get the reaction going. Okay. So we can see that a chemical reaction is happening. The phenolphthalein there just gives us some visible cue to the chemical reaction. That's the reaction of acetic acid with sodium hydroxide. Doesn't warm up nearly as much. So
I don't even know if that warmed up at all. The other reactions definitely warmed up. They're in fact still warm. But the vinegar reaction, not as much energy is released. The last one is going to be with sodium carbonate. So this is that gas-producing reaction where we're going to form carbon dioxide. For this one, we actually don't need any indicator, because the reaction itself, we can look for that little bit of bubbling that we saw. Right, so that's the carbonation, right? Forming carbon dioxide, reacting with the sodium hydroxide. Depending on how much acid I put in, it can take a certain amount of sodium carbonate. And if solid is left at the bottom, then we'll know I added too much sodium carbonate. Nice violent reaction there, lots of bubbles. You can see very clearly that production of carbon dioxide. As the concentration of the acid gets lower, because the acid is reacting away, the reaction gets slower and slower, and eventually it stops. And you can see that sodium carbonate in the bottom still. So I put in too much sodium carbonate compared to the moles of acid that were in there. The chemical reaction was really clear and obvious.
Our last set of chemical reactions are the redox reactions, reduction-oxidation reactions, which Dr. Neff defined in another video. In terms of predicting redox reactions, it's a little bit more challenging because most of the things we're looking at can have many oxidation states, many different possible charges. So in most of these cases, we need to know how the charge is changing. And that is, of course, the defining feature of redox reactions, is a change in charge. So when we're looking at this, this is going to be a silver with a +1 charge, a nitrate with a -1 charge, and a copper in its pure state, so it's got 0 charge. In the course of these things being next to each other, there's some energetic interaction. We go into more detail about that energetic interaction in Chem 125, 128. But there's enough energetic interaction that the copper is going to lose an electron to the silver, and we're going to end up forming silver metal. And we're going to end up forming copper nitrate. Now the catch is copper 1 or copper 2. What is the actual oxidation state of the copper that is being formed? In a Gen Chem course, the first time you're doing it, you can kind of just say, I'm predicting that some copper nitrate will form. As you go further along, you'll look at reduction potentials, and you'll figure out that that's going to be copper 2 nitrate. In most situations, we'll actually, copper 2 nitrate would attract 2 nitrates. That would be a +2 up there, -1 there. So 2 nitrates are attracted. This is copper 2 nitrate. So in this situation, I would need to tell you specifically that it was forming a copper +2 state in order for you to predict this product correctly in Tellem's order. In terms of balancing, that means we're going to need a 2 there so we can have our 2 nitrates, and a 2 there for our silver. The big tell for a redox reaction, there's a couple. Thing number 1 is if a different number of oxygens is attached to something, that's a good tell of a redox reaction. The name oxidation originally comes from considering where oxygens are in the reaction. The other big tell, going to more the electric tell, is the fact that copper is changing charge. Right? Copper goes from 0 to +2, and silver is going from +1 to 0. Right? Silver is gaining an electron, copper is losing electrons. So that means a good tell is whenever you've got a pure compound. Pure compounds with zero charge, we wouldn't write those there unless their charge changes. Let's look at another one. Magnesium metal reacting with oxygen. Right, and whenever we say oxygen, since it's one of our diatomic gases, it's going to be O2 in its natural state. That is also going to be a charge of 0. When these two things react, we're going to form magnesium oxide. Now, the magnesium oxide here, we're going to have that change in charge where that magnesium is a +2, that oxygen is a -2. We can balance the chemical reaction as well. So in this situation, oxygen has gained electrons. It is the oxidizing agent, but itself is reduced. Magnesium loses electrons, and magnesium is oxidized as it interacts with oxygen. Most of the times when we see these types of oxygen reactions, these are combustion reactions. Combustion is a special form of redox reaction, and we'll be looking at that more a little bit later. Again, pure things going to a compound. The last one I want to look at, because I think it's really interesting, we'll do this one as on the video as well, is sodium iodide, which sodium, so it's aqueous, plus aqueous chlorine. Let's leave the state of matter off there for a moment. Now, this is kind of interesting, because if you look at chlorine in terms of the intermolecular forces rules we learned last time, and we say, is chlorine soluble in water? Well, water is a polar compound. Chlorine has no difference in electronegativity. It's nonpolar. However, think to yourself, have you ever seen chlorine dissolved in water? Yeah, pools have chlorine in them. They don't like to have chlorine in them. That's why you can smell the chlorine. But we can slightly, under the right conditions, higher pressures, lower temperatures, things like that, we can force chlorine to be aqueous for a little bit of time. And that's going to allow us to make this reaction happen. Again, redox reaction. That chlorine, diatomic gas, so Cl2, is going to be its pure state. My sodium is a +1, my iodine is a -1. The likely thing that's going to happen, I know chlorine has high electronegativity on the periodic table, so I'm guessing that chlorine is going to pick up electrons. It's more electronegative than iodine. I'm going to see some change in that electronegativity, or not change in electronegativity, but change in charge because of the difference in electronegativity. And we are going to get NaCl- plus I2. Whoa, having trouble writing the letters. So we get Na still with its plus charge, Cl with its -1 charge, aqueous. And we form I2 with 0 charge. Iodine has lost electrons to the more electronegative thing, chlorine, and we've done a redox reaction. We've had that migration of charge, the motion of electrons from the iodine to the chlorine. Again, these are a little bit more difficult to predict. You do want to be looking at that difference in electronegativity, since this is about the flow of electrons and where the electrons are coming from and where they're going to. Looking for those electrons is going to be an important aspect of telling what's happening. Let's look at these reactions too. Let's go ahead and take a look at those redox reactions we just wrote down. So here is the aqueous chlorine solution. It doesn't look like much, but it does have that faint pool smell to it. And to that, we're going to add our sodium iodide.
aqueous solution, just a 0.1 molar, so that's the concentration of sodium iodide in here. And we should expect to see some chemical reaction. Now, think to yourself, have you ever seen an iodine solution? Have you ever seen places where they use it? Do you have an idea of what this should look like? If you've ever given blood and they've rubbed that kind of brown liquid over your arm before they do that little needle prick, that's an iodine solution. Iodine is used as a disinfectant, and it has a nice brown color to it. So as we put the iodine in, you can see just a little bit of color start to form, and then slowly over time, that color gets darker. Add a little bit more iodine, give it a nice shake. That's an iodine solution. The chlorine has become sodium chloride in solution, and that is iodine, I2, in the aqueous solution. Because I2 has a bigger electron cloud than chlorine, it's more soluble in water because it has a stronger London dispersion force than chlorine does. So this will stay. If I leave this out, eventually that color will disappear just as the iodine slowly leaves solution. But for the most part, this will stay a lot longer than the chlorine will. Now, for our next one, I want to set it up. It's visually very interesting but slow. So we'll be doing a time lapse for this one. And there's our redox reaction of silver nitrate with copper metal. What you have there are actual tiny spindles of silver metal. If we tried to take it out and collect it, you'd get a dust that is too fine to really collect. And honestly, the silver nitrate solution is more expensive than the silver you would get from it. But it is a really visually interesting reaction that occurs. If I give it a little shake, you can see the silver metal will fall away from the copper, and if I let this sit for another 10 minutes, that was 10 minutes by the way that just went by, we could form a little bit more silver metal, assuming that there's still silver metal left in the solution. So I think that one's pretty neat. It's slow. It's one of those things probably looks better with the speed up, but that's a redox reaction.